Hello and welcome to a new video on cryptography for everybody. In today's video, we will have a look at an actual attack on smartphones. And recently in the news, I saw that millions of Samsung smartphones could be attacked using an IV reuse attack. And I wondered how this was possible, so I had a look for the research paper. And you can see the first page of the research paper on the right side here. And it's a quite interesting paper, so I suggest that you read this. But in this video, I try to describe the attack or the basics of the attack. To do so, I structured the video into 4 different parts. In the first part, we will have a look at the AES GCM block mode. And that is a block mode that allows to use the AES as a stream cipher. How this works, we will see in the first section. In the second section, we will see an overview of the security architecture of Samsung smartphones. Then we will discuss the attack vector that was possible on these smartphones. And finally, we will simulate an attack as was implemented for the smartphones in Cryptool 2. Before we start having a look at the actual attack, we need to know what AES GCM block mode is. And the Galois Counter Mode or GCM mode turns a block cipher, and in our example here AES, into a stream cipher. If you don't know what block ciphers and stream ciphers are, I suggest that you have a look at the Basics of Cryptology series on this channel. And the Galois Counter Mode adds authentication to the encryption, additionally to turning the block cipher into a stream cipher. But this authentication is not important for the attack shown in this video, and it's not interesting for us. Here on the right side, I used a very nice picture from the Wikipedia that in detail shows how this block mode works. And as I said, the authentication part of that block mode we can completely remove here, so that's why I made it in or colored it gray. And as you can see, the basic idea of GCM encryption is that each block is encrypted by XORing an encrypted counter value with the current plaintext block to get the current ciphertext block. So you divide your plaintext into blocks. Then you have a counter. You can see the counter here, counter 0. This is incremented counter 1, incremented counter 2. And you go on that you reach the number of counter numbers as the numbers of blocks you want to encrypt. Then you encrypt each of these counter values using the block cipher, in our case AES. You get a ciphertext for each of these counter numbers. And you XOR the ciphertext that you obtain from the cipher with the plaintext to obtain the final ciphertext. And you do this for the second block, for the third block, and so on. So this basically turns a block cipher into a stream cipher. There's one problem with that. And when we use the same initialization vector IV and the same key, we will produce the same key stream. And this is crucial for the attack. Here you can see we have an IV. This is the start value for our counter. And when we have the same start value for the counter, then all these encryption blocks that we get here will be the same. This is a really bad problem, as you will see on later slides. Now let's talk about the actual Samsung mobiles. And here about the security architecture of Samsung smartphones. And Samsung mobiles are ARM-based. For example, the Galaxy S8, S9, S10, S20 and S21 were attackable using the here shown attack. And the basic architecture divides a smartphone into 2 parts. The first part is the Rich Execution Environment, or REE, and this is basically Android itself. And this allows to execute our normal apps that we have on our smartphone. And since it is very difficult to make all these apps secure, they invented, or Google invented, a second part, and that's a Trusted Execution Environment part. And this, for instance, only executes our security functions. So you only need to secure the TEE, So the parts that perform the cryptography, for instance. And the rich execution environment could even be not secure as long as TEE, the trusted execution environment, is secure. And with all modern processors, the ARM architecture itself supports the implementation of such secure hardware, or has a secure hardware part. And the security functions, so for instance, the cryptographic functions have to be implemented by the vendor of the phone. And here, of course, is Samsung, and Samsung implemented also the cryptographic functions in the TEE. Here's a nice picture showing both worlds. So we have our normal world, here we have our rich execution environment, and we have our normal apps like a calendar or a chat application and so on. So we have our apps here on the left side. Then we have the secure world here on the right side, which is secured by the trusted execution environment. We have security functions here, 1, 2, 3. And for us and for the attack, interesting is the so-called Keymaster TA. This is a hardware-backed keystore implementation of Samsung that is running in the secure world. And now when the normal world wants to use cryptographic functions, wants to generate a key, store a key, and so on, it uses an interface to the secure world to talk to the keymaster. The keymaster then performs the security operations and returns the results to the normal world. So we have two parts, a normal world and a secure world, which are separated from each other also by hardware. So it's impossible for the normal world to read or write or do anything to the secure world. It can only communicate via these interfaces. Now let's have a look at the actual attack vector. Sorry for all the text on this slide, but it's all important. So let's go through the slide step by step. First of all, we have to know that cryptographic keys on the Samsung mobiles are stored in so-called blobs. These are files in the rich environment, in the normal world. These are just encrypted keys, for example. A blob is encrypted using the AES Galois Counter Mode. And this is done by the keymaster TA in the trusted world or in the secure world. This looks like this picture here. So we have a key that we want to store in our key store on our mobile phone. So we give this key to the keymaster TA, which is running in the secure hardware part of the phone. This then encrypts the key, puts it in a so-called blob here, which is encrypted. So the key from this point cannot be accessed anymore from the normal world. And how does this work? When we have a new cryptographic key that should be stored on our phone, when it should be stored on the phone in the key store, it's given to the keymaster TA. Then the keymaster TA encrypts the key using the AES Galois Counter Mode to create the blob, and the blob is stored with the encrypted key in the normal world, in the REE. And to do so, each Samsung phone has a device unique 256-bit AES key called the root encryption key. So this differs from phone to phone. And each blob is encrypted using a hardware-derived key, HDK, that is derived from the RE key, so from the root encryption key. And here are two citations from the paper that are really interesting, I think, because these really show the flaws of the implementation. So the wrapping key that is used to encrypt the key blobs, the HDK, is derived using a salt value computed by the keymaster TA. So this is not bad. The keymaster derives a key based a salt and then encrypts it using it our key. But in version 15 and version 20 -S9, these are versions from the authors. The authors called these in the paper. The sort is a deterministic function that depends only on the application ID and the application data and constant strings, which the normal world client fully controls. So in the normal world, the client can define all these values, so it can control how this key derivation from the master key or from the root encryption key is executed. So by setting all the values to the same value, the derived key is the same. Of course, we have no access from the normal world to that key. We cannot access that key, but we can control the generation of the key, and that is really bad. And since we can do this, the security, so that there are different encryptions or different encryption performed for different keys, is only based on the security of the IV. So only when we change the initialization vector of our cryptographic algorithm of the AES Galois Counter Mode, the encryption would be the same. But here's another flaw, because additionally the caller of the keymaster TA, so from the normal world, is allowed to set the used IV, which is stored also in the blob. So when we give a key to the keymaster TA, we are in full control how the keymaster TA uses the cipher. We cannot decipher this here right now, but we can control how it is encrypted. So this is really bad. Because by choosing the same data and the same IV, we can basically enforce the keymaster TA to encrypt a blob using an already used key stream of an old blob we want to decrypt. And how does this work? So we have a blob, we don't know the key because it's encrypted inside the blob, but we know how it was encrypted. We know all the values that were given to the keymaster TA to derive the key for that blob, and we can control that. So how can we now decrypt this key here? And here comes an attack that probably a lot of viewers of this channel already know, and this is basically the misusage of a one-time pad, or as the authors of the paper call it, the reuse IV attack that leads to a generation of the same key stream. So what happens when we have a key stream used twice? You remember, we can force the key stream being generated the same way. So two blobs or their keys, that we call these plaintext B1, this is the first key, and plaintext B2, this is the second key. They are encrypted using the same key stream K, because the key stream K is only based on the IV and on the cryptographic key, and we can take care that these are the same for PB1 and PB2, so the key stream K, the generated one, is the same. Let's have a look how this works. So the cipher text 1 is generated by PB1 XORing with the key stream K. And if you don't know what XOR means, when you have data, for instance, you have here bits 1 and 0 and 1 and 0. When you XOR two ones, you get a 0. When you XOR a 0 and a 1, you get a 1. Here the same, 0 and 1, you get a 1. When you XOR two zeros, you get a 0. And using this XOR function, when you perform 2 times an XOR of a key stream on a plain text, you get the plain text back. You can see this here. First, we encrypt P. Here, we encrypt P using XOR of KS, and this gives us C. But when we then take C XOR KS, it's the same as P XOR KS XOR KS. That removes the key stream, and we get our P back. And this is the same as we have here. So when we use the same key stream again on our ciphertext B1, we get our plaintext B1, our key stored in the key store PB1. And when we do the same here for our second key, our second plaintext here B2, when we XOR the key stream on the ciphertext B2, we get our plaintext B2. Now we have two ciphertexts here, C1 and C2, both encrypted using the same key stream. And now is the problem, or the attack vector that we actually have. We can remove the key K by just XORing both ciphertexts C1 and C2. So we have, and this is CB1 and CB2, of course. When we XOR CB1 and CB2, we get basically PB1 XOR K XOR PB2 XOR K. And as you remember, we have 2 times here the K. As here with the key stream, we can just remove this. So we get the XOR of PB1 and PB2. So the key is completely removed. And remember, we don't know the key because it's stored. The actual key for the encryption of our key in the key store is stored in the trusted or in the secure computing part or hardware of our phone. But we removed the key, so we don't need to know K to get PB1 or PB2. Now we only need to generate a ciphertext where we know one of these two. So we generate a ciphertext where we know PB1, and if we know PB1, we can XOR this also on top of this last part here. So we remove PB1 and our result then is PB2. So basically we can get from each blob on the Android phone back the key, and this is really bad. The key stream generator in our case can be the most secure in the world. As I even said, a one-time pad would not help, because when a key stream or a one-time pad is reused, we can remove it easily to obtain only the plaintext. And if we know one plaintext, we get the other one. And yeah, as a reminder, with the Samsung phones, we were able to enforce encryption using the same key stream. Despite that the hardware is secure, it generates internally the same key stream that can then easily be removed. And one final note on this attack here is that the authors of the research paper reported the attack to Samsung Mobile Security already in May 2021, and they already discovered a lot of more besides that what I present here, and they reported the other attack vectors and possibilities in July 2021. And then since October or until October 2021, Samsung fixed the issues, including the removal of the key blob implementation at all. Now that we know how the attack basically works, let's simulate the IV reuse attack in Crypto2. And I have to tell you that right now we have no AES GCM implementation in Crypto2, but we can easily simulate the same attack just using stream cipher, because basically, as I said, the AES GCM block mode just turns AES into a stream cipher. So let's simulate the attack in Crypto2. I'm here now in the start center of Crypto2. I use the nightly build version 9.2.3.0.1, and I'm here in the start center, and I want to show you how the IV reuse attack basically works. And to do so, I just create a new workspace. And we want to use AES, so I search for AES here. And we want to use AES 2 times, so I just copy. Oh no, let's not copy it. Let's first configure it and then copy the configured one. So as I said, we don't have the Galois Counter Mode implemented right now in Crypto2, but we can use the output feedback mode, which also turns AES into a stream cipher. Now let's use text input here. So, and we will call this our first blob 1, since we want to simulate the attacks in the phone, and in the phone it's called blobs. Now we have to turn this blob here, this text here, we will use text for example, into a cryptool stream, since we want to encrypt it. And so I use a converter here, and I say this is a cryptool stream. Then we put this here and this here. So we have here our AES. Now we have to encode the AES data, and that's output from the AES. And I want to see this as hex values. And this here is the encrypted blob 1. And I have to change this to hexadecimal values. Now we need two additional things. At first we need a key for the AES. For that I just copy this here. And this is our secret key. We assume that we do not know this key. And we need 16 bytes, and I just use a very secure key. A, B, C, D, E, F, and 0, 0. And these are 16 bytes, but this is just a random key. Maybe later we just replace this by a random key. And this goes into the AES. And this is converter is wrong. We need a string decoder here. And I want to have hexadecimal. And this is our cryptographic key. And finally, we need an IV. And the IV, I just use this one here. And this is the IV. AES is set to 128 bit Padding mode 0s is also fine. This is hello world. And let's say this is secret key 1. And this is a secret key that we want to store in our key store. Now let's press play. And we have an encrypted blob here. Now, since we want to use we want to implement the reuse attack here, I just copy everything here, and I think I put this here, probably because I'm in the way. This is our secret key 2, and that you can see it better. I will increase this here and this here also. So we use the same key. So we can remove our secret key here. We can take the same secret key. Remember, we can control with the Samsung devices which key is used internally. And also we use the same IV because we also can control which IV is used. The only difference between those two ciphertexts that we will have here, the encrypted blob 1, we'll also make this bigger, and the second one, the encrypted blob 2, the only difference between those two is the key that we encrypt. Now let's have a look. And right now you can see we have secret key 1 and secret key 2. And yeah, as you can even see this here, only a very small part here should be different, and that is where the 2 here is. And the 2, 8, yeah, here we have 8b and 88. I think it would make more sense to use completely different keys. So let's for our simulation use a key that's complete A, or only A's. And here the same only for B's. So we use the same key and the same IV here. And we use an AES in a mode that turns the AES into a stream cipher. So we have this here is our first text. I stop this. So we take a second part here in the workspace. So this is our first blob, encrypted blob. And we don't even need the AES for the attack. So we have our first blob here. We have our second blob here. Copy the second blob. Let's even go further and just take a complete new workspace so that you see we don't need the AES for that. So we have our 2 encrypted blobs here. Now I need to convert this. These are hex values. I have to convert these to actual binary data. And that's wrong. We need the string decoder. And this here is hexadecimal values. Same for the second ciphertext blob. So this is, let's name these encrypted blob 1. And now we assume that we obtain this from the secure hardware of our mobile phone. And we have the same here, hexadecimal, hexadecimal. Now we need an XOR. And the XOR XORs both of our ciphertext. And in the background, of course, we know that the same key stream was used to encrypt our blobs here. We also assume that we don't know the first blob, but of course we know the second blob. Now when I XOR these two, and I just press play here, I get the XOR of these two ciphertexts here. This is now P1, or this is blob 1 XOR blob 2. We want to know the blob 1 since we don't know this, but we know that blob 2 and blob 2 we can just enter here, text input. And we know because we designed or we created blob 2 in a way that is just 16 Bs. Now we can use XOR again here we of course have to convert this also to hexadecimal, to binary data. This is text, UTF-8. And now we XOR our blob1 XOR blob2 with our known B2, blob2. So we get a text output here. And in the text output we will see blob1 XOR blob2 XOR blob2, and this is blob1. So let's press play. And of course, we have to convert this here also again to text. Because I don't want the hex values. This text UTF-8. Let's do it again. And here you can see our A's. So you see we have no AES at all. The AES was in our simulated, or in our simulation here, performed by the mobile phone, by the secure part of the mobile phone. We don't have any access to the AES, but we can control, and we go back to that workspace here, we can control how the IV and this, so we can control how the secret key is derived. We don't know the secret key here. This is unknown to us, but this is generated in the secure environment of the phone. We can enforce that the same IV is used, and that is the reuse attack of the IV here, of the initialization vector of our cipher. And then we obtain two encrypted blobs. We have these are files on our mobile phones. And when we just use two XOR operations, and since we know the content of our second blob that we created by ourselves, we can get the content of the first blob, the AAAs here. And these AAAs, in case of the mobile phones, were cryptographic keys. So we could get all the cryptographic keys from our phone, despite that we don't have any cryptographic key to decipher these keys. So this could have been a password, this could have been a cryptographic key. All that is stored or secured with these blobs and with the secure trusted hardware could be revealed. And this was because of the flaws of the implementation of the cryptography in the phones. As I said, Samsung fixed this, and of course the security researchers that found out these attack vectors, they informed Samsung before they published the paper. But I don't understand how someone can implement this today, since this is nothing that someone who has knowledge of cryptography would ever do. You don't create or the possibility to reuse the IVs in that. Yeah, that's just bogus. That makes no sense at all. Why this was in the phones, you can think on your own. I don't know why they did this. Nevertheless, I think this is a good example how good encryption like the AES can be implemented in a product, used in a product, but then be attacked because of such an error or mistake that they implemented here. Yeah, and this was everything that I wanted to show you in this short video. Now you know why you should never use the same IVs with stream ciphers, and AES was turned into a stream cipher. And I hope that was interesting for you, that you now know how this attack works. And yeah, if you did not yet subscribe to this channel, I would be really happy if you do so. This really helps me. This really helps me to grow this channel and to make Crypto 2 and the channel more popular. So thank you very much for watching, and see you in the next video.